NEC sections 250.20, 250.21, and 250.30 address the requirements for ground fault protection in separately derived systems. These sections mandate ground fault protection under specific circumstances to enhance electrical safety and minimize the risk of electrical hazards. However, a crucial exception is outlined in NEC section 250.21 A2. This exception provides relief from ground fault protection requirements for systems that exclusively supply equipment not powered electrically. This category primarily includes motors, which are mechanical devices driven by electrical energy but do not directly utilize electricity for their primary function. Considering this exception, a separately derived 240 volts delta circuit lacking a midpoint tap and solely dedicated to powering a motor load is not subject to ground detection requirements. The rationale behind this exception lies in the nature of motor loads and the reduced risk of ground faults leading to hazardous conditions. Motors are typically robust and well insulated, minimizing the likelihood of ground faults. Furthermore, the absence of a neutral conductor in a delta system, particularly one without a midpoint tap, further reduces the potential for ground fault currents. Therefore, the NEC recognizes that mandating ground detection for such systems would provide minimal additional safety benefits while imposing unnecessary costs and complexity. It is crucial to understand the specific requirements and exceptions outlined in NEC sections 250.20, 250.21, and 250.30 when designing and installing electrical systems. Consulting with a qualified electrical engineer or inspector is highly recommended to ensure compliance with all applicable codes and standards. It is important to emphasize that this exception applies only to systems exclusively supplying non-electrically powered equipment, such as motors. If the system also supplies other loads, such as lighting or receptacles, ground fault protection may still be required. The absence of a midpoint tap in the 240 volts delta system is also a key factor in determining whether ground detection is required. A midpoint tap provides a neutral conductor, which can create a path for ground fault currents. Without a midpoint tap, the system is considered ungrounded, and the risk of ground faults is reduced. The NEC provides detailed guidelines for grounding and bonding electrical systems to minimize the risk of electrical shock and fire. Grounding refers to the intentional connection of a circuit conductor to the earth, while bonding refers to the connection of non-current carrying metal parts to create a low impedance path for fault currents. These practices help to ensure that fault currents will safely flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. In addition to the specific requirements for ground fault protection, the NEC also contains numerous other provisions related to the installation and maintenance of electrical systems. These provisions cover topics such as wiring methods, overcurrent protection, and equipment grounding. Adherence to these requirements is essential for ensuring the safety and reliability of electrical systems. It is important to note that the NEC is a complex and constantly evolving document. The code is updated every 3 years to reflect changes in technology and industry practices. Therefore, it is crucial to stay informed of the latest revisions and to consult with qualified professionals when designing and installing electrical systems. In summary, NEC section 250.21 A2 provides an exception to the ground fault protection requirements for separately derived systems that exclusively supply non-electrically powered equipment, such as motors. This exception applies to a 240 volts delta circuit without a midpoint tap used solely for a motor load. However, it is crucial to consult the NEC and with qualified professionals to ensure compliance with all applicable codes and standards. The exception for motor circuits is rooted in the inherent characteristics of motor loads and the reduced risk of hazardous ground faults. Motors are generally robust and well insulated, minimizing the likelihood of ground faults. The absence of a neutral conductor in the delta system without a midpoint tap further diminishes the potential for ground fault currents. These factors contribute to the NEC recognition that requiring ground detection for such systems would offer limited additional safety benefits while adding unnecessary costs and complexity. While the NEC provides specific guidelines, consulting with a licensed electrical engineer is crucial for the design and implementation of electrical systems. Electrical engineers possess in-depth knowledge of the NEC and other relevant standards, allowing them to tailor designs to specific project requirements while ensuring safety and compliance. They can conduct thorough analyses of load calculations, voltage drop, and fault current to ensure the system operates within safe parameters. Furthermore, electrical engineers can provide valuable insights into energy efficiency and sustainable design practices. Understanding the nuances of the NEC and its application to various electrical systems requires ongoing education and experience. The code is constantly evolving to address new technologies and emerging safety concerns. Relying on qualified professionals is essential for navigating the complexities of electrical design and ensuring the safety and reliability of electrical installations. The NEC provides a comprehensive framework for electrical safety, but its effective implementation requires a combination of knowledge, experience, and professional judgment. Proper grounding and bonding practices are critical components of electrical safety. Grounding provides a path for fault currents to return to the source, tripping a circuit breaker or fuse and energizing the circuit. Bonding connects non-current carrying metal parts to create a low impedance path, preventing dangerous voltage build-up. The NEC specifies detailed requirements for grounding and bonding, including the size and type of conductors, the methods of connection, and the location of grounding electrodes. Proper grounding and bonding minimize the risk of electrical shock and fire, protecting people and property. In addition to ground fault protection, the NEC also addresses overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. This prevents overheating of conductors and equipment, reducing the risk of fire. The NEC specifies the appropriate size and type of overcurrent protection devices for various circuits and equipment. Selecting the correct overcurrent protection is crucial for ensuring the safety and reliability of electrical systems. Wiring methods are also a critical aspect of electrical safety. The NEC specifies the types of wiring methods that are permitted for different applications, taking into account factors such as voltage, current, and environmental conditions. Wiring methods include conduit, cable, and raceway systems. Each wiring method has its own advantages and disadvantages, and the selection of the appropriate wiring method depends on the specific requirements of the installation. Proper wiring methods ensure that conductors are protected from physical damage, moisture, and other environmental factors. Electrical safety is a shared responsibility. The electricians, engineers, inspectors, and homeowners all play a role in ensuring the safe operation of electrical systems. Education and awareness are essential for preventing electrical accidents. By understanding the basic principles of electrical safety and following the requirements of the NEC, everyone can contribute to creating a safer electrical environment. In the context of motor circuits, understanding the specific characteristics of motor loads is crucial. Motors are inductive loads, which means they store energy in a magnetic field. When a motor is switched off, the stored energy can be released back into the circuit, causing voltage surges. These voltage surges can damage electrical equipment, so it is important to protect motor circuits with surge protection devices. Motors also draw a high inrush current when they are started. This inrush current can be several times the normal operating current of the motor. Overcurrent protection devices must be sized to accommodate the inrush current without tripping unnecessarily. The NEC provides specific guidelines for sizing overcurrent protection devices for motor circuits. Variable frequency drives are often used to control the speed of motors. Variable frequency drives can improve energy efficiency and process control. However, variable frequency drives can also generate harmonic currents, which can cause problems in electrical systems. Harmonic currents can overload neutral conductors, overheat transformers, and interfere with electronic equipment. The NEC addresses harmonic currents and provides guidelines for mitigating their effects. Power quality is an important consideration in electrical systems. Power quality refers to the characteristics of the voltage and current waveforms. Poor power quality can cause equipment malfunctions, reduce energy efficiency, and shorten equipment life. Power quality problems include voltage sags, voltage swells, harmonics, and transients. Power quality monitoring equipment can be used to identify and diagnose power quality problems. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Power factor correction can improve energy efficiency and reduce electricity costs. Power factor correction is typically achieved by adding capacitors to the electrical system. Electrical maintenance is essential for ensuring the safety and reliability of electrical systems. Regular inspections and testing can identify potential problems before they lead to failures. Electrical maintenance should be performed by qualified electricians. Electrical safety training is important for all workers who work with or around electrical equipment. Electrical safety training should cover topics such as lockout-tagout procedures, arc flash hazards, and the proper use of personal protective equipment. Arc flash is a dangerous phenomenon that can occur when electrical equipment is energized. An arc flash is a sudden release of electrical energy that can cause severe burns, blindness, and even death. Arc flash hazards can be mitigated by following safe work practices and wearing appropriate personal protective equipment. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout procedures involve disconnecting the equipment from its power source and attaching a lock and tag to the disconnect switch. The lock and tag prevent anyone from accidentally energizing the equipment. Personal protective equipment is used to protect workers from electrical hazards. Personal protective equipment includes items such as gloves, safety glasses, and arc flash suits. The proper use of personal protective equipment can significantly reduce the risk of electrical injuries. Electrical safety codes and standards are constantly evolving to reflect changes in technology and industry practices. It is important to stay informed of the latest revisions to these codes and standards.